This is a short series of video presentations on computational generative grammar that I have been using in my own linguistic and cognitive scientific research. The reason I originally came up with this idea of doing this or using this video format for this material is because here it's easy for me to illustrate everything by using concrete examples. For example, almost everything that I will be covering in these lectures will be ultimately implemented in Python programming language. And so here, as you can see, it's easy for me to illustrate how they actually work. I can run these scripts. I can show you how we work with concrete linguistic data, and so on and so forth. So I think this video presentation is quite a useful format here. A few words about the background requirements, what kind of content I will be discussing, and how much background knowledge and competencies will be required for the listener. So this is first of all computational generative grammar. The term itself implies that there are going to be a lot of discussion of computational methods. And when it comes to computer programming, Python in particular, that I will be using in these lectures to illustrate and implement everything, I will be assuming basic understanding and basic competence in those topics. So this is not going to be a tutorial on programming, object-oriented programming, or Python specifically. I will have to assume that the listener is familiar with those. This doesn't mean that you will have to be a software engineer because or have advanced knowledge of these topics, because when we apply computational methods into scientific research, empirical research, then that is the main focus, and the computational part, the engineering part, takes a secondary step. It's just a tool which helps us accomplish certain things that are difficult to complete or accomplish by using paper and pencil, for example. So yes, I will be assuming basic understanding of programming and Python, but nothing extraordinary, nothing very advanced. And all the examples I've created for these presentations, they are going to be as simple as possible. Then the other thing, the term computational generative grammar, there is the term generative grammar. That term simply refers in this connection to linguistic and cognitive science research that is unambiguous, rigorous, and formal. But when it comes to the, let's say, the fundamental assumptions underlining these fields, linguistics and cognitive science, and all sort of hybrids of the two, I will again have to assume that the listener has a basic level, at least basic level of understanding of what's that all about. Preferably PhD level understanding at least. In other words, I'm not going to cover in a great detail how this type of research is conducted, how to read publications of the primary scientific literature, and so on. But that being said, when I will be discussing the computational generative grammar, which means application of a certain type of computational methods into linguistic and cognitive scientific research, that specific topic, then I will make almost no assumptions. In other words, in that hybrid domain, this is going to be extremely elementary, and I will try to create these presentations in a way that doesn't assume anything from the listener. Everything is, at least I try to explain everything from the ground up. To summarize, you will need some basic understanding of programming and Python to understand the final implementations, and then you should have some knowledge about empirical linguistics and cognitive science, preferably PhD level, or at least a master's thesis on these topics. So this is not an introduction to those things, but it will be an introduction to the hybrid combination of computational techniques in that type of research. You should be able, after going through these presentations, to start or develop or design your own computational generative grammar research project. You should be able to begin to build your own tools and to apply them to your own data. So that's the background that I will be, or at least what I try to maintain throughout these presentations. Now let's go to look at a little bit of the contents. I have created, at this point I have created 15 presentations. We should be seeing them here. Let's see, yes, they come there. The first one is this introduction, no need to say anything else. Then the lecture 2 and 3, I will be talking about linguistic data. Sorry, I skipped the lecture 2. So the number 3 and 4 is about linguistic data and the creation of data sets for the purposes of, for the research purposes. But lecture 2 is more fundamental philosophical or philosophy of science topic. I'm going to be discussing a methodological principle that underlines this whole enterprise. I think this is something that it's anyway useful to make completely explicit before we go on. This is the principle, I saw it already here. So the idea is that if we have some data, in this case it's going to be linguistic data or cognitive scientific data more broadly, and then we create a theory or a hypothesis for that data. We assume that we must show that the data follows from the hypothesis. In other words, what we try to explain follows from what we use for the explanation. And why this is so important and so meaningful, or let's say significant principle. Well, first of all, in linguistics, almost nobody makes this assumption as it is done in present day. So we will have to do some thinking and some work in order to implement this in a very rigorous way. But the difficulty and the non-trivial part here is that if we want to, first of all, if we want to have a theory, if we want that something follows from our theory or hypothesis or grammar, whatever it's called, then the grammar, hypothesis, or theory has to be completely unambiguous. If your theory is ambiguous, if it uses informal terms, ordinary English, or technical concepts that are not defined in a completely rigorous way, then of course nothing really follows from that, because we don't even know what this theory is saying ultimately. And the same concerns the data part here. We will have to do things a little bit differently because if we don't have, if the data doesn't exist in some type of explicit closed data set, again, then of course if there is no data in that, if the data doesn't exist in that form, then we can't show that it follows from anything if it doesn't even exist. So we will have to do some amount of work there also. And finally, the more important part is that when we have an unambiguous theory, then its logical implications are also all determined. They kind of exist in an objective sense. in the same sense that if we have a mathematical formulas or axioms, then their logical implications come into being in some implicit way. But here we have to show, actually demonstrate that the data we have follows from our theory. So we have to somehow construct the proofs also. We have to prove that the data, that the hypothesis is justified by the data. And all these steps therefore have to also be unambiguous. So we are not satisfied with sketches, or we are not satisfied with the assumption that I believe that the data follows from the theory. We have to show that it actually is the case. That requires some amount of non-trivial work, especially in our field where the proofs can be quite complicated. But this is the topic of the presentation too. This is going to be all philosophical or informal discussion. And then, as I already told, the number 3 and 4 about data, as I just mentioned, we need to be a little bit more careful in how we create the data and how we present and create the data and data sets in order to apply this methodological principle. Lecture 5 is about complexity barrier. That's the main reason we will have to employ computational methods, namely because the relationship between the theory and data is so complex due to the combinatorial nature of both, that the only way we can literally show and justify the theory or hypothesis or grammar is by employing computational techniques. The type of complexity we encounter there is still quite trivial to handle for a standard computational methods, and this is the fundamental reason we will end up using this type of computational formal methods. But that's still not, I will not be going into these concrete methods yet in the lecture 5, and also lecture 6 is still going to be more informal. I'm talking about enumerative recognition grammars. These are the two types of generative grammars that we can create. And they're slightly different approaches, not in a mathematical sense, but empirically. So it's useful to distinguish the two. Finally, then from lecture 7 onwards, we move to discuss more concrete computational issues and implementations. I will begin with this derivational search function. It's a kind of a fundamental core of the whole computational infrastructure. That's the system that will bridge the data and theory in a rigorous way together. It's a simple function which will be with recursive function that will do that. In fact, it was already here. I noticed by chance the whole function is actually already visible here. It's just a small piece of code that will create a bridge between the theory and data. Whatever data, whatever theory. This will be presented in a way that the whole material here will be presented in a way that doesn't depend on any particular grammatical theory or hypothesis. It's the same principles whether you do minimalist grammars or cognitive linguistics or pragmatic-based research. That doesn't change this approach. So that's how I have created these example implementations. Well, let's move on here. As you can see here, I have divided this presentation into two parts, 1 and 2, and that's because the part 1 is concerned with the more broader issue, the overall topic, and the presentation is still quite informal. And then part 2 is always the Python implementation, the actual computational implementation of the topics that I covered in part 1. And all of these lectures, the 3 lectures here, are organized in that way. Lecture 8 is about supervision management, and I noticed that I sometimes confused. I'm talking about management and maintenance. I confused the two, so let's call this supervision, management, and maintenance. This is about creating enough computational infrastructure that we can handle all the complexity that is involved when we start this type of research. And it's also the layer in the computational infrastructure that will be creating permanent records of the proofs that are going to be generated. It's an important topic that has to be discussed, not because it's interesting for the research, for the empirical research itself, because you need these layers in order to create a useful computational infrastructure for actual practical research purposes. Lecture 9 is, I remember it was slightly longer because it's a complex topic about how we work with several languages, and this is more complex because here we start to talk also about language acquisition, universal grammar, and language learning, language acquisition, and parameters, and that's a very challenging topic to discuss even without the computational techniques. But everything we cover there will be again transformed into a more rigorous setting in part 2. Lecture 10 is about graphical user interface. It's about supervision, maintenance, and management again. And then lecture 11, 12, the 11 well, what happens here is that up until this point, I simply assume that we have some notion of lexicon available, lexicon referring to the words, list of words in the language. But in a real research, that is too simple assumption, so we have to do some work. And this lecture I'm discussing how to take various theories of the lexicon and again transform or map them into the more rigorous computational context. And the same we will do the same for the notion of phrase structure in lecture 12. So if you are listening to these presentations and you notice that I'm freely talking about the lexicon and phrase structure, then what I mean is that those notions are first assumed to be, they are presupposed, and then later we return to those issues in more detail. There is a reason why I wanted to do it in this way, and it is because these are very controversial notions in the actual empirical theory. So it didn't make sense to introduce this type of controversies before we have covered all the basics of the computational methodology itself. Lecture 13, we are just going to discuss the notion of derivational search function in the context of a class of recognition grammars. 14 is about resource consumption. Here we are covering some issues that have to do with performance, language use, and real-time processing, things like that. And finally, the lecture 15 is complex topic about morphological parsing again in the context of a class of recognition grammars. It's a complex topics. Now here in the lectures 11 to 15, we will be going through some empirical hypotheses or theories, and that the topics are empirically controversial. But I'm not going to make any empirical claims. So I tried to create this presentation so that it's possible to that I cover a wide variety of approaches, and I'm not limited to some one particular approach. Well, that's the contents at this point. It's possible that I add later some more advanced topics, but it seems to me that this should be enough to get things going, to get a basic understanding of these methods. As I pointed already, I have used myself these methods in my own research for some 5 or 6 years now. But there are several publications and papers where they are applied mostly to Finnish linguistics and Finnish language, which is my own I'm interested mostly in Finnish language, and I'm myself a native speaker of that language. But in those papers, the more fundamental properties, it's not possible to cover the more fundamental properties in research papers that have to be focused on the empirical issues. So this video presentations kind of gives a background of what's underlining or what is in the background and the context for those actual research papers. Well, then I had here a couple of points that I wanted to conclude with. The first is the language of these presentations. Now, I had two choices in the beginning. I could try to use my own native language, Finnish, would be much more easier for me. I would be much more fluent. I would not make so many mistakes. My pronunciation would not be annoying. And I tried to do one of these videos in that by using Finnish. So then there would be an automatic translation for those who don't speak Finnish or understand Finnish. But that didn't really work out well because for two reasons. One is that a lot of this terminology and theories that I'm going to discuss are the original terms, and the concepts and theories they exist in English. The main terminology is in English. And so sometimes it became difficult to find the Finnish terms, and also I would need to think to invent this type of terminology in my own language, which I'm not interested in doing, and it just makes things more complicated. And the second reason was that the automatic translations were not accurate enough. They were not precise, and already because of this terminological problem. So I decided in the end to use English, although my English is quite bad. I make mistakes. My pronunciation is not good. It's not native. It's not fluent. So my speech is kind of slow when I have to pedantically think through everything and then use tortured English language to express them. But the upside of this is that now I can fully control what I'm saying, and I know that what I'm saying comes out exactly as I want it to say. I can be very precise on how I describe these things. It's very important in this type of context where we are talking ultimately about very rigorous formal computational things. So that's why I'm going to do this in English, even though the result doesn't sound so good to me. But perhaps we can forgive this problem. And a final thing I wanted to point out is that although we are going to be applying computational techniques to linguistics, to language processing, to linguistic data, what I'm going to talk about here is not the same as computational linguistics as an engineering discipline, as an engineering field. So we have automatic machine translation. We have large language models creating able to maintain pragmatically intelligent conversations. And we have a machine learning more generally, data science. That is not the topic here. Those are things which are completely different. Their goals are completely different from us, and the problems they encounter in those fields are totally different from the problems that we have to solve here. So what I will be discussing here is simply basic theoretical and empirical linguistic and cognitive scientific research as it exists in primary research literature. And then we will be applying computational techniques to that kind of research to help us solve specific problems in those fields and in those domains. And so we are dealing with scientific research, basic scientific research, attempt to understand how languages and the human mind work, and not creating engineering applications for specific purposes, for pragmatic purposes. I will be covering some of these differences in the lectures 3 and 4, but not much. But it's important to understand that what I'm saying here doesn't have any interest or application in the domain of engineering. And the type of computational concepts and examples I will be going through here, they are so basic, I don't think that they will help anybody who is interested in becoming a software developer or who wants to learn machine learning or to use artificial intelligence or create large language models. Where I do think that this could be potentially useful are those listeners who are, for example, beginning their PhD projects, research projects, and would like to apply computational techniques to their research problems and in those fields where they work.